The other kind of incremental syntactic processing effect that we'll look at today is garden pathing, which you're already familiar with from previously in the semester. To review, here's an example of a garden pathing sentence. When the dog scratched the vet with his new assistant, removed the muzzle. Now, you saw this sentence once before earlier in the semester, but you still may have the same subjective experience that you had earlier on, which was that this sentence is surprising and difficult to understand at a very particular point. And probably for you, it was at the word removed. So to remind you why this happens, notice that there's a very appealing incremental parse of this sentence where the dog scratched the vet with his new assistant is a clause. In particular, it's the clause that is introduced by the subordinator when. But that's actually wrong. In fact, the vet with his new assistant removed the muzzle is actually a clause, and there is a clause boundary which is not explicitly marked after the word scratched. Because of the incompatibility of the incremental parse where the vet with his new assistant is the object of scratched, removed is very hard because your preferred incremental parse is not compatible with incorporating removed into the tree at that point. And so you have difficulty at this point. You can contrast this with a case where if the word scratched were followed by a comma demarcating the end of the subordinate clause, then actually things typically are not so difficult. When the dog scratched, the vet with his new assistant removed the muzzle. Now at this point, this potential interpretation where the vet with his new assistant is the object of scratched is blocked by the comma, rendering removed easier. Now we can contrast these examples with another set of examples that are identical, except I'm going to substitute the verb scratched with the verb arrived. When the dog arrived, the vet with his new assistant removed the muzzle. This is no longer so hard because arrived is an intransitive verb. It doesn't take an object, and so there's no reason to think that the vet with his new assistant would be the object of that verb. Rather, that's pretty obvious even before you get to the word removed, that the vet with his new assistant is the beginning of the main clause. And so whether or not you have the comma here doesn't matter so much. So we're going to actually convert this garden pathing behavior, and this garden pathing behavior is also something that we see in humans. I'll show you some human processing data at the end of today. We're going to convert this pattern, this set of 4 examples, into a test of human-like syntactic processing behavior for neural language models as follows. So we're going to take all 4 of these examples and let us understand and think about these examples as a 2-by-2 manipulation of 2 properties. Whether or not the first verb that appears in the sentence is transitive. In the first 2 cases it is, in the second 2 cases it's not, because scratched is transitive, arrived is not. And whether or not the verb has a comma. The first and third examples don't have commas marking the end of the last of the subordinate clause. The second and fourth examples do. And it is the interaction between these 2 things that creates a particular kind of processing difficulty, because the interaction of one choice of transitivity and one choice of having a comma or not creates this garden pathing effect. In particular, A is superadditively more difficult than any of B through D. So the difficulty of both having a transitive verb and not having a comma is greater than the effects of transitivity or of not having a comma alone. So we will assess this effect by looking at the surprisal at the word removed given the context. So in all 4 conditions, let's define the surprisal S of X as that's shorthand for the surprisal or negative log probability of the removed given the context of whatever version X is. So in particular, this will lead to a couple of predictions that we want to have for human-like processing behavior. One is that the surprisal that S of A, the surprisal of removed given the context in version A, should be larger than the surprisal of removed given the context in version B. This is because having the comma there should ameliorate the processing difficulty encountered at removed. And another criterion is that the surprisal at that effect, the difference of surprisal between A and B, should be reduced by changing the verb from scratch to arrive, because you've now made the verb intransitive. So we have the second prediction is that S of A minus S of B is greater than S of C minus S of D. There's actually a third prediction that we can make here, which is that the surprisal of A is also greater than the surprisal of C. I won't note that explicitly on the slide, but keep in mind that prediction, because on the next slide, you'll see that that one also turns out to hold for these models. So first, I'm going to show you a sort of human word by word or region by region reading time like graph for surprisals. That's in this graph. So this is a graph of the mean surprisal in each region of the sentence where we've demarcated the regions in an intuitive way. And we have the 4 conditions in a 2x2 layout. So dotted lines are with a comma, solid lines are without a comma. Red is transitive subordinate clause verbs, and blue is intransitive subordinate clause verbs. And actually, you can spend some time offline looking at this graph a little more carefully. The more you look at it, actually, it's extremely interpretable in terms of what the effects of context should have on word probabilities for all of these models. But we're going to focus attention on just the critical region of potential garden path disambiguation removed. So first of all, you'll notice that the solid red line is the highest in all of these models. And that's the transitive no comma version. That was version A, which we expected to be the most surprising. So that actually is a broad success. We'll also see that the distance between the red line, the solid red line, and all the other lines is different for the different models. And I want to zoom in on in this region by, once again, looking at the effect of the comma, which is going to be the solid versus the dotted version of each line for each of the 2 conditions for each of the models. And that's going to be the effect of the comma, or we're going to call that the size of the garden pathing effect for each of these models. That's what's shown here. There's the size of this garden pathing effect, the without comma versus the with comma. So the surprisal of the without comma version minus the surprisal of the with comma version. So remember that the 2 criteria are, first of all, that in the transitive version, this should be greater than 0. Because adding the comma should make things less surprising. And second of all, the difference between having a comma and not should be smaller for a transitive verb than for an intransitive verb. So you can see that all of these models succeed in the first prediction. In particular, they have a non-zero garden pathing effect. One thing you'll notice is that the size of the garden pathing effect is larger under 2 conditions. One is when you have models with more data. So more data seems to lead to a robust, bigger overall surprisal effect. And then the other one is having grammar versus no grammar for a small data set. These are the 1 million word data sets, whereas both the LSTM alone model on the right and the RNNG model on the left have a basic garden pathing effect in the transitive condition. It's a larger effect for the grammar-based model. The second thing to look at is whether that effect is decreased by changing the verb from transitive to intransitive. And it turns out that that doesn't really happen very much in either of the models with small amounts of data. Even for the grammar-based model, there's not a very big effect of verb transitivity, and there's an even smaller effect of verb transitivity for the model that doesn't have explicit grammatical structure. On the other hand, the models that have larger amounts of data do have a robust effect of verb transitivity. And what that suggests is actually an important point about the way that neural models learn and generalize. So it turns out that actually, once again, even with a very small amount of data, with just 1 million words, you can learn gross facts about syntactic state, even with a model that doesn't have any explicit syntactic structure, like tiny LSTM, but that gets more robust when you actually have explicit syntactic representations. And those effects are quite manifest in incremental processing. However, for finer grained things, like the relationship between what word you are and what kind of syntax you like to have, you really need to get more data in order for those robust effects to occur more robustly. So once you get 1, 2, or 3 more orders of magnitude of data, then even without explicit syntactic state representations, you can actually get quite human-like syntactic processing behaviors, even when lexicosyntactic contingencies like is a verb transitive or not are involved. So that's the first set of results for NPZ garden pathing. The second one is another question that I want to address, which is the following fact. So this is a different set of configurations of these kinds of ambiguities. Here, what we're manipulating is, first of all, whether or not there's a comma blocking the garden path. But here, we're always using transitive verbs. But the question is, how much material is there between the beginning of the syntactic ambiguity and the resolution of the syntactic ambiguity? In all cases, the syntactic ambiguity begins when you have the beginning of that noun phrase, the book, that might either be the object of wrote or the subject of the main clause. In conditions A and C, those are short, conditions A and B, That's a short condition where the book is a short phrase, and so from the onset to the end of the potential ambiguity is only a couple of words. In conditions C and D, those are long conditions. There's a lot more material that intervenes. And you could imagine one possibility is that a model that sort of has the beginnings of syntactic state-like representations but that are not very robust might not be able to maintain those distinctions between an ambiguous condition like C and an unambiguous condition like D over a long stretch of text. Everything might become a messier soup as you progress farther and farther on into a sentence. That's one possible hypothesis. To test that, we're going to look at, first of all, we're going to ask what the prediction is. So for a human-like pattern would be, and you'll see in a moment, it would be that the syntactic distinction between having the ambiguity, like in A and C, and not having the ambiguity, like in B or D, is actually robustly maintained. Humans maintain robust syntactic hierarchical structures over long stretches of text. A human-like processing pattern would make a prediction like the following. First of all, there would not necessarily be a qualitative difference in the effect of having the comma or not on the processing difficulty at the word grew. So the target word here is the word grew. So S of X is the conditional probability of grew given the context. So S of A minus B might not be very different from S of C minus D, but they should both be positive because in both cases there's a garden path that the comma can block. Well, we'll see what behaviors the model actually shows. So here's all the four models again. First of all, in all cases, they do still have a garden pathing effect. These are all above 0. But now notice something interesting. So two of the models do fully robustly maintain the garden path effect over this longer stretch of text. It's the biggest model, the model with 800 million words of training data, and the model with only a tiny bit of training data, but with some explicit syntactic state information. In contrast, the medium-sized model and the small sequence-only model, the LSTM-only model, don't as robustly maintain garden path syntactic state ambiguity effects over this longer stretch of text. The long condition garden pathing effect is smaller than in the short condition. Now, I actually want to just spend a moment before we end for today, just actually telling you a little bit about how this works in humans, in particular the latter effect. So this is an experiment which is not exactly the same experiment as I showed you on the previous slide, but it's very close. So here the manipulation is, once again, it's a 2x2 manipulation. We either have a long stretch of text, like in C and D. We have a couple of extra words that are intervening in between the book and the disambiguating region grew, or A and B is a short condition where the book is immediately followed by grew. And now, instead of a comma being used to block the potential garden path, in conditions B and D, there's an explicit object for the verb wrote, and in conditions A and C, there's not. Okay, and so the bottom is a self-paced reading, word by word graph. This is work by Tabor and Hutchins in 2004, and what you see is the following pattern. Once again, we might have the prediction that that the effect of transitivity is there for both of the short and the long cases. Now here's what we see. So there is actually a small effect of verb transitivity in the, of having an object in the A versus B condition. It's there, but it's quite small. Interestingly, in the human data, increasing the length of the ambiguous region actually increases the processing difficulty effect that occurs when you have garden path disambiguation. So the most difficult condition here is actually not the highest surprisal condition for the artificial models. The human most difficult condition is actually the one, this condition C, where there was a garden path ambiguity, and then people had to revise and correct the misinterpretation only after a longer stretch of text had intervened. So they had to maintain both interpretations, or at least the possibility of revising to this book is the main clause subject interpretation, and achieve it here after a longer intermediate region. And so that is not the same processing effect as we see in the artificial systems. So the surprisal pattern in the neural language models does not capture the human digging in effect. And this is one example of a broader set of points, which is that a wide variety of human incremental processing effects in syntactic comprehension emerge automatically from a high-performance contemporary neural language model with surprisal as the linking function between conditional word probability and processing difficulty. However, not all incremental human language processing effects can be captured simply by surprisal as the linking function. And we'll see more of these kinds of effects in future classes, but this is one instance of it. So to summarize, for the NPZ garden pathing cases, here's what we saw. We saw that all models show evidence of a syntactic garden path effect that can be blocked by a comma. Even models that are just an LSTM trained on only 1 million words. These kinds of syntactic state-like effects actually show up very quickly in neural language models. In order to get modulation of that effect by individual verb preferences for being transitive versus intransitive, you have to have a lot more data. Having explicit syntactic state alone doesn't really actually seem to help that much. What really matters is a lot of data. Third, not all of the models robustly maintain syntactic state-like distinctions over long stretches of intervening material. Having a huge amount of data seems to help with that. Having explicit grammatical representations also seems to help with that. That's the end of today. And next time we're gonna go on and continue on in this vein. Thanks very much, and looking forward to talking with you tomorrow.